Welcome to part 2 on characteristic subgroups. In the last part, we defined a characteristic subgroup of a group G to be a subgroup of G that's fixed under all of the automorphisms of G. We also showed that every characteristic subgroup of a group is normal, but not every normal subgroup of a group is characteristic. In this video, we will look at examples of characteristic subgroups. We first note that in practice, if we have a subgroup H of a group G and we want to show that H is characteristic in G, it actually suffices to show this weaker condition that for an arbitrary automorphism of G called alpha, we have that alpha applied to the subgroup H is actually contained in the subgroup H. So this is, on the surface, this looks like a weaker condition than this. But we will argue as follows that it's actually equivalent. To start with, note that if alpha is an automorphism of G and alpha of H is contained in H for alpha arbitrary, then this just means that alpha of H is contained in H for all automorphisms of G. Now, as alpha inverse is an automorphism of G, we recall that this forms a group under function composition. Then this just means that alpha inverse of H is contained in H. And now, if we apply the identity automorphism of G to H, we just get that H equals the image of H under the identity automorphism of G. This identity automorphism just equals alpha composed with its inverse. And then we get that that equals alpha of alpha inverse of H. This is contained in alpha of H because we note here that alpha inverse of H is contained in H. So we know that this part here is contained in H. So this whole thing here is contained in alpha of H. And then alpha of H is contained in H by this point. So what we've actually shown is that H is contained in alpha H and alpha H is contained in H. Therefore, alpha H equals H, so H is characteristic in G. So with that in mind, let's look at some examples of some characteristic subgroups. First, note that the identity element is always fixed by any automorphism of G. So in particular, the trivial subgroup of G consisting of the identity element is characteristic in G. And note that clearly the entire group is fixed under any automorphism of G. So the entire group is characteristic in G. For our next example, we will prove that the centre of a group G, this is equal to the set of all elements X in G that commute with all of the elements of G. We'll show that this is characteristic in G. So let X be in the centre, G be an element of the group G, and alpha an automorphism of G. If we can show that G alpha of X equals alpha X of G, i.e. that alpha of X is in the centre of G, then by the previous slide, that's enough to show that the centre is characteristic in G. We do this as follows. G alpha of X equals the following. We note that alpha composed with its inverse applied to G gives us G back, so we can write G as this. And then we note that alpha is a group homomorphism, so we can take this product inside. Now we note that X is in the centre of G, so we can change the order of these two group elements. And now once again we note that alpha is a group homomorphism. And then once again we note that this result holds, so we get that this equals this, i.e. we get that G alpha of X equals alpha X of G, and we've shown that the centre is characteristic in G. For our next example, we will show that the derived subgroup of G, also called the commutator subgroup of G, is characteristic in G. Recall that the derived subgroup of G is the group generated by all of the commutators of G. These are all of the elements of the form GH, G inverse, H inverse for elements G and H of our group G. Note, to show that the derived subgroup is characteristic in G, it suffices to show that the image of any generator under any automorphism of G is contained in the derived subgroup of G. So let G and H be elements of our group G and alpha an automorphism of G. Then the image of this generator here under alpha equals the following. And this holds because alpha is a group homomorphism. We can then take these inverses outside, again because alpha is a group homomorphism. And then we note that this element here just equals the following commutator, which is contained in the derived subgroup of G. So we've shown that the derived subgroup, or the commutator subgroup of G, is characteristic in G. In the next video, we will show that the Frattini subgroup of a group G is characteristic, and an extra result on CELO theory.